7, 6, 5, 4, 3, 2, 0. And liftoff of the Atlas V. Launching the first...
Norwest Christian School in New South Wales, Australia, collaborated with Salam Community School in Dubai about ways that they could capture carbon from rockets.
So you were looking at carbon capture out of the rockets expelling carbon, and so these were all the ways that we could look at carbon capture from the ground, so through moss and algae and seaweed.
So these are just kind of we discussed using like plant waste or just plants in general. It'll be efficient in terms of capturing carbon instead of emitting it.
How do we capture the carbon after it's been expelled from the rocket? So that's why we went with, okay, well, we look at carbon neutral. What does that look like? So that's this list at the top. How can we make it carbon neutral? So yes, we're going to expel carbon when we burn these fuels. How can we then be doing other things to capture that carbon? And then we sort of looked at, okay, well, what about different alternative rocket fuels that don't expel as much, and that sort of thing. So
yeah,
it was so nice to meet you.
Yeah, it was really nice.
Meanwhile, Salam Community School in Dubai further investigated how rockets might pollute and affect our atmosphere.
A common question that has been recently ruled out in the space industry community is whether rocket emissions actually pollute the atmosphere or cause some sort of change in climate change. Well, the answer depends on different differentialities, which play a certain role or factor in determining the answer to this long-awaited question. Research papers and atmospheric analysis has been conducted to find the actual answer to this question. Moreover, these factors are, for example, the amount of payload versus the amount of exhaust emitted, the atmosphere you're in, or which mid-atmosphere you're at, where your gases are going to be. Will they be emitted above the atmosphere or in orbit? Will they stand as space debris? Or what type of gases are you emitting? Or what is the rocket exhaust fuel? What is the rocket oxidizer? And internally, what is the rocket engine? Or what type of rocket? What use is it going to be? So these questions all determine the answer to the question that I said earlier. We're going to be focusing on these factors as well as determining the effect of black carbons on climate change, as well as their impact and how they can potentially affect the atmosphere. So black carbon emissions are usually forecasted to be greenhouse gases. So let us discuss the gases and what they are and how they affect climate change. So for example, pollutants of the climate change are carbon monoxide, sulfuric oxides, as well as nitrogen oxides. Ozone depleting gases are like alumina, chlorine, nitric oxides, and greenhouse gases are like carbon dioxide, nitrogen oxides, water vapor because they absorb heat, and sometimes soot. So, let us discuss. So for instance, in solid rocket boosters, usually aluminum oxides, soot, carbon dioxides, hydrochlorides, nitrogen oxides, and trace gases are produced. A lot, really. Then we have the hydrolox emissions, which are hydrogen and oxidizer rockets, and these emit, as you guessed it, water vapor and water. Then we have RP1 Kerolox emissions, which are kerosene and oxygen oxidizer emissions, which emit carbon dioxide, water vapor, nitrogen oxides, carbon soot, and carbon monoxide. Then we have one of my favorites, the methyl emissions, which are methane and oxygen rocket engines, which produce carbon dioxide, water vapor, and nitrogen oxides. What is the radioactive forcing, and what does it mean for us? Well, radioactive forcing is the amount of energy that is being stored as greenhouse gases on our Earth versus the energy that is actually being radiated outwards. Okay, let's talk more about black carbons then, if they cause this tropopause folding. Well, it takes about roughly 3 to 5 years to get all of this black carbon emitted out of our atmosphere. And really, this is why the effects last longer on the stratosphere. The stratosphere has high ratios of about 10 parts per million compared to the troposphere, which has about 0.1 parts per million, affecting the ozone layer. These thermal gradients should prevent these mixtures, but due to the amount of tropopause folding, harmful constituents like black carbon, methane, and nitrogen oxides can usually sink due to the rockets being through the stratosphere and the troposphere. Now, tropopause folding usually happen between them, and this is basically just air being injected from that tropopause, from the troposphere and the stratosphere. And this is another reason why the stratosphere holds more of the everlasting effect. So, right now, our current technologies and the way we look at BCs, or black carbons, isn't entirely understood. Okay. Now we said that tropopause folding mixes these and puts them underneath in the stratosphere as an everlasting effect. What if I tell you that currently hydrocarbon fueled rockets, actually the black carbon does not stay in the dense areas of the stratosphere, but rather goes to the orbit at which it was emitted? Well, that is kind of weird because we said that it goes to the dense atmosphere, the stratosphere. Well, this brings us to a conclusion that we don't yet understand black carbon movements, and that is why it's very important to study them and their sensitivity. Now, for example, they have more stratospheric burden than aircrafts emitting these black carbons. They also have a shortwave absorbent, as we said earlier, which means that they're more sensitive to the ozone layer, and they all have a higher warming effect than carbon dioxide because of how sensitive they are by a factor of propellant per unit. In this decade, radioactive forcing has exceeded from carbon dioxide by a factor of 100,000 per 10,000 launches in the decade. Now, this is extremely a really high value, and it does tell us a lot about our future of using these hybrid fuels.